So what I'm going to talk about now is some of the algebra that's involved in geometric modeling. And I'm going to organize it in a similar way to the previous lecture. We'll do curves first. Talk about what's called the degree formula. We'll talk about Syzygy's implicitization, and then Riesz algebras that were mentioned briefly by Carlos on Monday, and talk about how they relate to implicitization. And then we'll switch to surfaces, where there's a degree formula, but there's a new gadget called a base point that causes complications. We'll talk about Syzygy's and implicitization, but we'll have to work affinely. I'll talk about resultants and sort of the effect of base points, and then we'll talk about this idea about matrix representation as an alternative to implicitization. And so that's the plan. So I'm going to start off with the geometry, and so here I'm going to take three polynomials, but normally you might think of something like x equals a of t over b of t, y equals, oh, that's a c. So you might think of an affine parameterization by rational functions, but what we're going to do is basically work projectively. And so that means that I take A, B, C, they're not going to be homogeneous polynomials, all of the same degree. And so that degree is always going to be n. And then I'm always assume their GCD is 1. So it turns out that if I simply map ST to ABC evaluated at a point in P1, I get a point in P2, and this GCD condition says that's going to be well defined, and the image will be some curve. And here the field I'm going to work over will either be the rational numbers, real numbers, or complex numbers. And so, for example, think about when the weighted Bezier curve in the plane. So here we had points in the plane, and so here's the formula I had. Remember, the weights mean we have to divide by this to make it to preserve the convex hull property. And so here's this rational parameterization of a curve in the plane. But of course, when I stick that in projective space, a point in the plane, I add on, basically the coordinate infinity, and I homogenize. And then what happens is when you take this and homogenize, well, this, I have to add the 0.1, but then it's homogeneous coordinates, so I can clear the denominators. This crops up here. When I homogenize, I just get a nice polynomial parameterization. And so this then, and remember that pi is actually a point in the plane, and so this is actually three homogeneous polynomials of degree n. And so this guy is an example of that guy. And the degree formula is that, so here we have our situation, and there's 2 degrees involved, because of course, I'm thinking of just the curve being parameterized in the plane. That has, its degree, and that's basically, the degree of the irreducible homogeneous polynomial that defines the curve. But also the function might have a degree because, it's a number of points that map via phi to a generic point of the curve. An example would be this very simple parameterization, and it's generically 2 to 1, because, for example, ST and minus ST map to the same point. And it turns out that, of course, the sum of these two guys, so x plus z, is just equal to y, so I'm just parameterizing a line. And so the degree of phi is 2, and the degree of the curve is 1. And of course, what the theorem says in this hypothesis, where the degree n with the GCD is 1, the degree n is always the degree of the map times the degree of the curve. And of course, in practice, you often want that to be degree 1. And so the idea is that you want phi to be birational from the P1 onto the curve C. Now, implicitization, so the terminology is that the equation of the curve is called the implicit equation, and implicitization is the process of going from the parameterization to the implicit equation. And it's a problem in elimination theory because, because when I think of this projectively, I have, basically I want x to equal that, I want y to equal that, I want z to equal that, so I want all those to equal 0. And so basically I want to eliminate s and t to get the implicit equation. And of course you can do that using Grobner bases. It's beautiful in theory. Sometimes it can be slow in practice, although there are people that will disagree with that. If you ask Daniel Lazard, he said Grobner bases are great for implicitization. And there's actually even some recent work by Abbott, Bugatti, and Robiano on implicitization of hypersurfaces using Grobner bases. So there is some. So this is not something to be ignored. But for this particular talk, I'm going to focus on other kinds of algebra that you can use for the implicitization process. So now let's think about this curve parameterization thing from an algebraic point of view. So what's going on algebraically? So I again take my 3 polynomials of degree n, GCD is 1, and they'll generate an ideal now in our polynomial ring. And then by the Hilbert-Syzygy theorem, this has a free resolution. So there's the ideal, and then when I sort of, there's 3 generators, so I have to map r cubed onto it, and that minus n is the usual bookkeeping to keep this to be a map of degree 0. And then what happens is the Hilbert-Syzygy theorem says when I sort of, in this situation, because I've only got 2 variables and I'm working homogeneously, that puts a limit on how long the resolution can be. And so in fact the kernel of this map actually has to be free. Then you do a little Hilbert polynomial calculation and you discover that this free module has the twists are minus n minus mu1 and minus n minus mu2, and the sum of these mu's has to be n. And it's in geometric modeling, it's customary to set the smaller of these to be mu, and then of course the larger will then be n minus mu because their sum is n. Now it turns out the existence of this kind of free resolution was first proved by Meyer in 1887, and he actually did it in exactly this case of 3 homogeneous polynomials of degree n. Now, I tried to read his paper and failed, but the one thing I could read is the footnote. And in the footnote, he talks about how he thinks this should be true for any number of generators, that he tried really hard to prove it and couldn't. So he had this sort of ad hoc argument that worked only for 3 generators. And then in 1890, this guy named Hilbert publishes a big paper where he does the Hilbert-Syzygy theorem, and his very first application is to prove Meyer's conjecture. And in fact, that's how I found this, because when I became involved in this, I said that this looks pretty basic. It should be somewhere early on. So I tried Hilbert, and there it was in Hilbert. And Hilbert, of course, then led me to Meyer. And so that's how I figured out the sort of the genealogy of this. And of course, the general idea of Syzygy's, so now here, let's think of R as just an arbitrary commutative ring, and then I take a bunch of elements of my commutative ring, and then I can just talk about the Syzygy module, and that's just basically, you take all elements of you sort of take R linear combinations that are equal to 0 and just take, what coefficients do that for you. So this is going to be an R module, and it in general can be a really complicated gadget. So the fact that in our case, so the Syzygy module is the kernel of that, and so right here, this says that the Syzygy module is free, and its generators are going to be the mu and n minus mu. And in fact, the basis of this is often called a mu basis. And so this is what makes the curve case so nice, is that you really have a free Syzygy module, so that gives you a lot of good information about what's going on. Now, here's some more recent history connected with this. So I mentioned on Monday this paper by Anderson, Sederberg, and Goldman, and they basically, implicitized curves, just using the classic, Sylvester resultant. But then in 1995, Sederberg and Chen introduced an interesting idea, that you imagine a line in the plane, so they're working affinely, a line in the plane where the coefficients depend on a parameter. And so the idea is that, if the parameter varies, I get a moving line. So this is the idea of a moving line. And of course, when I write my parameterization this way, working affinely, the parameterization is a moving point. So you can imagine the idea of a moving line that follows the moving point. Well, when does that happen? Well, that means that here's the moving line, and when I plug this into that, I should get 0. And when you clear denominators, you get exactly that equation right there. Now, about a year later, Syzygy and Chen realized that there were basically 2 moving lines, and from these 2 moving lines, you should be able to get all of them. And then in 1997, Syzygy asked me, David, have you seen this equation? And I always love it when somebody asks me a question where I know the answer.
They probably like it too.
Yeah. And I said, yes. And I said that, this means that the capital ABC is in the Syzygy module of the little ABC. And then Tom asked me the question I expected. What's a syzygy? And, I got to explain that, astronomy is syzygies. It's the alignment of 3 celestial bodies in a straight line. And then Sylvester loved introducing strange terms into math. He introduced a whole bunch. I mean, he catalectant is something that he liked, and syzygy is something he liked. So he did permanent. Yeah. So all sorts of stuff. And so I answered that question. Then he asked me, what's a module? And I realized, to me, that's such a natural language of stuff. And here's Tom, whose work has involved vectors of polynomials ever since his PhD work. He had no idea what a module was, because his training was in mechanical engineering. So the applied math he learned, basically there was no algebra in it. The closest he got was linear algebra. And so that sort of, to me, is one of the challenges for, as we're trying to sort of export this stuff as applications. People in the applied world still have a somewhat narrow view of what math you need, and there's a lot of algebra, and it doesn't mean the algebra has to be deep or hard or stuff, but it's a great language for talking about stuff. And so that's something the math community needs to think about. Like, even how do you teach the graduate algebra course? Are you only trying to train the future algebraists, or are you trying to give all of your graduate students a language they can use no matter what field they end up in?
Yeah, I think narrow it has negative connotations. We couldn't find a better word than that to describe the background.
What?
Narrow has negative connotations.
Yeah.
It's not anybody's fault that they don't know this stuff.
Right, exactly, yeah. And then what happened is that, so after the conversation, they basically said, hey, there are these two that generate, and so I sat down and wrote a proof, and using the Hobart-Syzygy theorem. So the question is, why did it take me 6 months? And it's sort of embarrassing, but this happens. It'll happen to you sometimes. Because of course they asked me this question in this affine context. And so I wasn't thinking projectively, I was thinking affinely. And one thing I know is that in this case, when you're A, B, and C as polynomials in one variable, if their GCD is 1, then they generate the unit ideal. And the one bit of algebra I knew in that case is the Kazul complex is exact. So I basically goofed around with that and was able to prove the theorem. But then I realized that, well, what's going on is that they were really interested in, because, affinely, it's, if you just look at the Syzygy module, saying it's free is sort of pretty obvious, and it's basic modules over PID. It's torsion free and finite, it has rank 2, so it's got to be that. But there's lots of bases, but they wanted minimal bases. So I was trying to think minimal bases. What makes degrees minimal? Well, maybe when you homogenize, that's important. And then maybe when you homogenize, you're dealing with a homogeneous ideal. Oh, then maybe the Hilbert-Syzygy theorem applies. So what should have taken me about half an hour took me 6 months to figure out this is actually trivial. But done 100 years before. And so in 1998, so this is my first paper in applied math that I wrote with basically Syzygy and Chen, and we introduced the mu bases, and so published in this sort of really fun journal, and so that was sort of my entree into this geometric modeling enterprise. And now let me give a couple of formulas for doing implicitization. And so the first thing is, so I'm going to add one more caveat. I want to assume that these guys are linearly independent. because if A, B, and C are linearly dependent, well, that means you're parameterizing a straight line. That's like really boring. And what that means geometrically is this mu, the minimum degree of a non-zero syzygy is at least 1. So the idea is you don't have a constant syzygy. And then in this case, there's a regularity result, and we'll see, we'll eventually give a very easy reason, that it turns out if you look at the syzygy module in degree n minus 1, there's exactly n things in it. So let's take a basis. So again, these are the syzygies where basically the dot product of this with that is equal to 0. And now let's turn them into the moving line. So I just take the dot product with x, y, z. And then this is a game we played on Monday where you take, because remember the a, b, and c, these are all polynomials in S and t, and they have degree n minus 1. So let's rewrite it as a polynomial in S and t. It's a homogeneous, of course, and where the coefficients now are linear forms in x, y, z. And so notice the numbers. The numbers are nice because of that n, I have n linear forms. So I goes from 1 to n, and then the j goes from 0 to n minus 1, and there's very conveniently n of those. And so when I assemble all these guys into a matrix, it's a square matrix. Now on Monday, I was doing a slightly different kind of thing where we played the same game. We took some syzygies, we wrote them in terms of the S and T and assembled them into a matrix. Monday was a more complicated situation. In this case, I just have this beautiful matrix, and it's n by n. They're linear forms, so its determinant has degree n. So this determinant is a polynomial of degree n, and in fact it's exactly the implicit equation to the degree of the map, and of course this side also has degree n, so it all fits together very nicely. So that's sort of a first implicitization formula that really uses the moving curves. But remember that you really only should need 2. And and the question is, why did they, when they had this all these moving curves, why did they think you only needed 2? What was the geometric reason? They weren't thinking about ranks of free resolutions and stuff. They were thinking geometrically. Why do I need 2 moving lines? Well, the idea, and remember, right now we have n of them, so that's. But why do you need 2? Well, let's take a moving line. So here's a line, and then at a slightly later parameter time, here it is. So this line is moving sort of in this direction. And then here's my second moving line moving in this direction. But remember that we also have the moving point of the parameterization, and in any parameter value, the moving point is on the corresponding moving line. So this parameter, so that for a fixed parameter value, that moving point is on this line and this line. So it's the point of intersection. So when I take the 2 moving lines, when I follow their point of intersection, that is the parameterization. So that's the geometric way that they were thinking that I should use only 2. And then what we proved in our paper is that if you take a mu basis, so the question is which moving lines do this most nicely? And of course, it's the basis of the syzygy module. And then it turns out there's 2 things that happen, is that from the moving lines, you can actually reconstruct the parameterization. And there's 2 ways to think about it. You can think of, because each of these, it's a syzygy, so each of these has, it's a vector of 3 entries, so this is a 2 by 3 matrix, so you can take its maximal minors. And, or you could just take the cross product, thinking of these as vectors, and again, that boils down to maximal minors. And so it turns out that, so your parameterization up to a constant is really just the maximal minors of, the matrix you get from the mu basis. But then also, I can think of these as polynomials in S and T, because, this has degree mu in S and T, that has degree n minus mu in S and T. And so when I take the resultant, thinking of these as polynomials in S and T, well, and what happens is that, of course, that has degree mu, that has degree n minus mu, and of course the coefficients involve x, y, and z, and so you get this beautiful formula because you end up taking the determinant of an n by n matrix when you do the Sylvester matrix, and so you get exactly the formula we had before. So the resultant of a mu basis gives the implicit equation up to the degree of the parameterization. And of course, 1 is actually again, really goes back to Hilbert, and he actually states this fact. For him, it's Cramer's rule, and so he states that in his 1890 paper. And then Birch is the one that sort of brought it into the modern commutative algebra way of thinking about it. And then, how do we get this result? Well, remember that we were able to use the Syzygy module in degree n-1, but we have a basis. That has degree mu, so I have to multiply it by polynomials of that degree to get degree n-1, and this has degree n minus mu, so I multiply it by that. And so that's what this Syzygy module looks like in degree n-1. Now remember, I needed a basis of it. Well, how do I get a basis? Well, I just take the monomials of this degree and multiply it by p, take the monomials of this degree, multiply it by q, and then when I take their coefficients, you get exactly the Sylvester matrix of p and q. And so the determinant of the previous slide for this nicely chosen basis is exactly on the nose the resultant. So that's very pretty. And we're going to see this idea about the sort of implicit equation is the resultant of a mu basis. That has some interesting echoes in the surface case. But there's also another bit of algebra. This is again something that like Carlos mentioned is in his lecture is the Riesz algebra. So we have an ideal in the commutative ring. The Riesz algebra, it's just basically, it's this graded ring. We're in degree 0, it's the ring. Then in degree 1, it's I. Degree 2, it's I squared. Degree 3, it's I cubed, and so on. And the way you often write this is sort of you add this auxiliary variable e, and so then you can actually write the Riesz ring as a subring of the polynomial ring in one variable e over the ring R. And it turns out that this way of thinking makes it easy to think about how to give a presentation of the ring. Because how do you know what this ring is? Well, you want to know, basically you'd like to write this Riesz algebra as a quotient of a polynomial ring by some ideal. And so if your generators are G1 through GL, then I'm going to use L variables, and I take this polynomial ring in R with those variables, and I just map xi to gi times e, and it turns out that you just completely naturally get a map from this ring, and it surjects, its image is exactly the Riesz algebra. So then really all I have to do is understand the kernel of this map. And in commutative algebra, these are sometimes called defining equations of the Riesz algebra. And of course, the relation to Syzygy's is, well, the point is, if I have a Syzygy, then when I turn it into, notice it becomes an element of this ring, then, again, when I take this and evaluate it here, being in the Syzygy means that I'm actually in the kernel K, but it's degree 1. So 1 refers to the grading in the x variables. And so basically the Syzygy module is basically the degree 1 part of the kernel. And it turns out that for example, if you happen to be in a super nice case where your polynomials are a regular sequence, in fact, K1 generates all of K, and so you're done. So basically, in the case when you have a regular sequence, life is just wonderful. And then this is in gray because it's not super relevant now, but it is important for other things. Hal's going to mention some of this. If I take if I take this polynomial ring and mod out by k, the full kernel, I get the Riesz algebra. If instead I multiply out just by the stuff generated by the Syzygy's, you get the symmetric algebra, which is another canonical gadget that's done. And basically the tension, a lot of the difficulty of understanding Riesz algebra is sort of the tension between the symmetric algebra and the Riesz algebra, and this is sort of where approximation complexes enter the picture. And so that's something we'll learn about in Hal's lecture. But now that's algebra. Let's think about the modeling aspect. So again, it's our usual thing. And so here's a definition from the Sederberg and Chen paper of 1995. So you take a bihomogeneous polynomial. So you'll have degree I in S and T, and it'll have degree J in X, Y, Z. So I'll write the bi-degree as that. And then suppose I fix the point ST. Then if I just fix the point st, then this just becomes a homogeneous polynomial in xyz. So I'll define a curve in P2 of degree j. But then I take that curve, if I then start varying my point in projective space, I get a moving curve. So before we talked about moving lines, and that's where this degree j was 1, but now we allow moving conics, moving cubics, so basically moving curves of arbitrary degree. And then the idea is that, we talked about already about that Syzygy is a moving line that follows the parameterization. Well, suppose you had a moving curve that follows the parameterization. Well, that means that, when the parameterization is given by x, y, z equal those. So basically, to follow the parameterization means that this point is on the curve, so that's got to be identically 0. That says exactly that I'm in the degree j part of the kernel. So the degree j part of the kernel are the moving curves of degree j that follow the parameterization. So so basically the geometric modeling community basically discovered the kernel of this map or the defining equation of the algebra where they found it in a purely geometric context. And then the question is, why were they interested in this? And the answer is there were some interesting moving curves that weren't just moving lines. And so let me give an example. And so first of all, also this is just a way to compute it. And you see I have an algorithm for computing it. So here we want the kernel of this map. So this is in the curve case. Well, so what do I have to do? Well, I could first think about basically, because remember x is mapping to, the generators are a, b, c. And so the map here sends x to that, y to that, z to that. So if I sort of think about in the situation, if I were to add this extra variable e, then the kernel is just that guy. But I want to get rid of e. So I basically have to eliminate e. And that's elimination theory. So basically I have to just simply take this ideal and do that. And so you compute a Grosvenor basis and then to a suitable term order and take the intersection and you're done. You can also automate this in Macaulay too. And so for example, and here what I want to do is, so see here's, I'm going to work over Q. We saw that yesterday in Jose's demonstration. And here are the variables. And I want a monomial order that's going to eliminate the first variable. So I want something that's going to eliminate E. And then J1 is just basically this ideal for that particular parameterization. So that's the ideal. And then what's the next step in my algorithm? Well, I want to do this in Macaulay 2 efficiently. I am not great at Macaulay 2, so my algorithm is I ask how. Now, I would not recommend that for you, because if Hal starts getting 60 emails, they get really angry at me. But there's a lot of really cool commands in this. So you take this one, you compute a Grosvenor basis, you do the generators, then select in subring, and so that means basically you're getting rid of the stuff that involves E, and then you look at the ideal, look at the minimal generators. And this gives a matrix, although Jose gave some cool commands that you can use instead just to get a list of the polynomials. So you get a list of 5 polynomials that are the minimal generators. So these are the defining equations of the Riesz algebra. These are the minimal generators. So for example, right here, you get ones, you see these have just degree 1 in the x, y, z. So these are the moving lines. And notice they both have degree 2, and that's because mu is equal to 2. And since n is 4, so basically both p and q both have degree 2. So one of these is p and the other is q. And so you have that. Then here, notice that now the degree in S and T, so it's gotten here it's degree 2 in S and T, here it's degree 1, but I've got degree 2 now in the XYZ variable, so these are moving conics and that follow the parameterization. And then so you get 2 moving conics, and then finally you have the implicit equation. So I just degree 0 in the parameters. If you think about it, this is a moving curve that doesn't move. And so that's certainly always in it. And so the idea is that you start with the mu basis, and that's really what you're interested in. And it turns out this is an interesting intermediate step to get there. And so for example, here's a theorem for n equals 4. And so And let's assume that our parameterization is birational, so our curve is genuine quartic. So the degree of C is 4. Turns out the only possibilities for mu are 1 and 2. Remember, we're assuming they're linearly independent. And also it turns out that people understand that, how singularities do. And in this case, if you have a singular point, the only possible singularities have multiplicity 2 or 3. And it turns out that mu is 2. And so this is a result of Sederberg, Goldman, and Dew, that mu is 2 if and only if the singular points all have multiplicity 2. And also, it turns out that, what they did in their papers, they identified these guys. So they knew that you had these two interesting, the mu basis, you had these two interesting moving conics at degree 1, 2. They had the implicit equation. And they also knew that they could get the implicit equation just by taking a 2 by 2 determinant of this. That's something Carlos mentioned on Monday. So here you end up with basically a 4 by 4 determinant expressing f in terms of the Sylvester resultant. But once you go here, it's only a 2 by 2 determinant. So this is so once you get the moving conics, you get the implicit equation very quickly. Then what I did in 2008 is basically say that in this situation, in fact, these 5 that you've identified, in fact, always generate, so these are the minimal generators of the kernel, so these give the defining relations. And it turns out there's also an internal structure that, for example, if I take P and Q, and if I express them in terms of S and T squared, I'm going to get a little 2 by 2 matrix. And when I take the determinant of that 2 by 2 matrix, I get one of the moving conics. And when I express P and Q in terms of S squared and T, play the same game, the 2 by 2 determinant gives me C2. These are called Sylvester forms now. And then, of course, when I take, this is what I mentioned earlier, if I simply take these guys in terms of S and T, because they're linear in S and T, and so then there's another 2 by 2 determinant that gives the implicit equation. And so the fascinating thing is that it's just starting from P and Q, I can actually generate all the minimal generators and end up with the implicit equation in sort of this iterative process. And whether or not you can do this in general is still a work in progress. So there's cases where we know what's going on, cases where we don't. So here's another one of the results. So this is a paper I did with Bill Hoffman and Hao Wang. And so again, it was classically known for a long time that when mu is 1, that's if and only if it has a unique point of multiplicity 3. And then in this case, there are, again, 5 defining equations, so 5 minimal generators for the kernel. And it turns out that, since mu is 1, so you get 1 and 3 for the degrees of the mu basis. And then you get only one moving conic, then you get a moving cubic, and then you get the implicit equation. So it's a slightly different constellation of minimal generators, but turned out there's a similar internal structure for Sylvester forms, and this works actually for any time u is 1. Doesn't have to just be when n is equal to 4. It can be general n. And many people have written papers on this. There's relations to the singularities, and there's a long list of names. And this long list of names will be on the board during Hal's talk, and you can also find many of these people mentioned in the lecture guide. So this is a rich, interesting area, and there's some unsolved problems that either Carlos or I will probably present on Friday, because there's a lot of stuff we want to know about this. But now let's turn to surfaces, because there's a whole raft of stuff to say about surfaces. And so let's think about an affine case. So here's, now S and T are affine parameters. They're no longer homogeneous. And so now I map to a point x, y, z. And so x, y, and z are now rational functions of S and T. And again, you often want to try to make this projective, but one of the big things that happens in the surface case is there's many ways to make things sort of projective, to sort of add points at infinity. And one way is just to classically homogenize. So I'd add another coordinate 1 here, sort of at infinity. I clear the denominator, so that gives the s squared plus t squared, and then I'd homogenize the other guys with respect to u. So now I just get a nice polynomial parameterization. Everybody has degree 2. But I could also take each of these individually. Instead of using P2, I could use P1 cross P1, and so you get this particular one. You could also use other toric surfaces. So there's situations where you actually want sort of the Newton polygon of these functions to actually tell you what polygon to use, and that'll tell you what toric surface to use, and that'll be sort of your domain for sort of a projective version of the parameterization. And typically we assume that A, B, C, D, because there's, in this case there's going to be 1, 2, 3, so that's A, that's B, that's C, and then D is the common denominator. So that's the setup we're going to use. We typically assume they have no common factors. Now in the curve case, having no common factors meant they couldn't vanish simultaneously. But in the surface case, even if they have no common factors, you can still have base points where all 4 vanish simultaneously. And this might even happen over at infinity, when you go to this kind of thing. And even if you're working over R, you can have base points over the complex numbers. And it turns out you have to worry about all of them to try to make sure you have the correct viewpoint. So for example, in this case, well, notice that when S and T are both 0, notice that everybody in sight vanishes. So 0, 0 is bad. And it turns out that in this case, when I sort of make this one projective, that's the only base point I have. But in this case, sort of the 0, 0, 1, that's the 0, 0, 1, but I also sort of have a bad base point at infinity. And so in this case, I happen to have 2 base points. And so the number of base points you have can be affected by sort of what compactification you use. And that's often how you, and for example, if you use the Newton polytope, that often gives you the most efficient one that will minimize the number of base points, but it might not get rid of all of them. Now there's a degree formula, and the degree formula has, so we're parameterizing a surface, it'll have a degree. And also the parameterization map will have a degree. And so these two are similar to the curve case. But now, of course, we have the base points. And so basically the variety where all A, B, C, D vanish. So those are the base points. And each base point has what's called a, and so my hypothesis that A, B, C, D are relatively prime, that means there's finitely many base points. So these are isolated points. But each of these has a Hilbert-Samuel multiplicity. And so the degree is built from, so basically, in this case right here, when I homogenize, I get homogeneous polynomials of degree n when I'm going from P2 to this. And I notice that here it's a rational map because there might be base points, might not be defined everywhere. And so basically, I get an n squared, I get the product of these degrees, but then I have correction factors coming from the base points. And again, here I have to work, even if I'm thinking about this over the real numbers, I have to count complex base points, I have to count base points at infinity to make sure you get the correct answer here. And then it's almost the same in this case, except that, of course, my domain is P1 cross P1, so you get a slightly different formula. And, of course, these are now become bihomogeneous of degree mn, and so that's how they affect the degree of the image. And you have a similar fact that the base points sort of, in a sense, they sort of reduce the degree. And in some cases, base points are bad, but, they also lower the degree. That makes things easier to compute. So they're also not, they have some good features as well. And I want to say just a tiny bit more about the proof of this, because notice that n squared and that 2mn, well, it turns out that's really Bezout's theorem. And so, if I had P2, 2 curves of degree n, that's the number of points of intersection. If I have 2 curves here of by degree mn, that's the number of points of intersection by Bezout's theorem. So that part is the Bezout's theorem one. And to really get a handle on this one, there's some serious commutative algebra. I do not know a totally elementary proof. In fact, the elementary proof I know uses reduction ideals from commutative algebra. Now, if that's the elementary proof, what's the other proof? And the answer is you read about Syzygy classes and Fulton's intersection theory. And there is a proof there. And so you read it carefully. It's all there. It works out. It's beautiful. And so, like I say, this is a case where, you see that algebra is really asserting its influence in a pretty serious way. So let's do this example. And in this example, it turns out the surface just thinking affine needs a surface of degree 3, so the degree is 3. It turns out that you can actually check without difficulty the parameterization is generically, it's a birational parameterization, so the degree of phi is 1. And then when I look at this way, there's only one base point, and you can check that the Hilbert-Samuel multiplicity is 1. And so when you do the stuff, well, these are guys of degree 2, so I get the n squared is 4, then subtract the Hilbert-Samuel multiplicity, so I get the 3, that's what I like. But if I use this one, mapping from P1 to P cross P1 to S, well, I have two base points. And it turns out one of the base points has Hilbert-Samuel multiplicity 1, the other is actually got multiplicity 4, and but it turns out that the bi degree is 2, 2. So it says degree 2 in S and U, it has degree 2 in T and V. And so you get, so the 2nm is 2 times 2 times 2, so that's 8. But then when I subtract off the multiplicities of the base points, I get 5, so I still get the 3. So it doesn't matter which model you do, provided you count the base points and the multiplicities appropriately. So that all fits together very nicely.
I should point out that formula at the top here, just where you get the degree from some intrinsic degree minus some base points, that's also behind this rational linear precision.
Yeah.
That difference is 1. And that explains, in a sense, why it's so rare, because the center of your projection has to be very, very singular, like maximally singular with respect to your torque writing.
I see, yes. I want to ask you about that later.
Sure.
About, so now let's think about this more geometrically, because remember, so far I've been doing the algebra, so let's think about sort of some of the syzygies, because they were certainly interesting in the curve case. So in this case, and I'm going to work affinely, and so the idea is that, so here's a plane, and assuming that A, B, C, and D are not all 0, and but then if I let these be polynomials in S and T, then I get a moving plane. And of course, here's my parameterization. And so, of course, to follow the parameterization, when I plug this into this, it has to vanish identically. When I clear denominators, I get that. So in fact, in this situation, the moving planes lie in the Syzygy module. And it turns out in this particular affine case, and so this is special to the affine case, is that I still have a free Syzygy module and of rank 3. Because in the plane case I had 2 lines intersect in a point, and that's why I had 2 moving lines that gave the parameterization. Here I have 3 moving planes, but 3 planes should intersect in a point, and that should give the surface parameterization. We'll see that's a picture that has to be modified a little bit, but turns out there's some complications, because in this affine case there's no good notion of a minimal basis. So in fact there's infinitely many bases. They can have arbitrarily high degree. So it's not at all like the projective case. There's no notion of a minimal basis for a free module. And also it's just a lot harder to compute. This is sort of related to the Serre conjecture. A finitely generated projective over affine space is free. Finding that free base is not easy. You can't just plug it into Macaulay 2 and say min-gens. And so this is something that's a little, so it's not as nice as the curve case. So I'm going to focus on the affine case because I want a mu basis, and so so here's these guys generate the Syzygy module, and then also I'm going to often think about it as a matrix, and then we still have the Hilbert-Birch theorem, which says that the 3 by 3 binars with the suitable signs really are the parameterization. And now one thing that's important here is to realize that so here's a matrix. I've got the 3 by 3 minors. Well, a base point is where these guys all vanish. That means the 3 by 3 minors all vanish. That means this guy drops rank. So here we're now, we're in a rank dropping situation of a matrix. We've seen that idea before, so that's actually pretty interesting, and that's something we're going to exploit in the next few slides. So that's pretty good. And let's do an actual example. And so here's a very nice case. And in this case, there are actually no base points. And even when you homogenize and make it projective, and there's an affine mu basis that's given by this. There's the projective version. But it turns out that if you compute the Syzygies of this, the Syzygy module is not free. In fact, it has 5 minimal generators.
How do you compute a mu basis?
The answer is I forget. I did it so many years ago, and somebody else did the computation.
If you're lucky to get to that point in your life.
That's right. And so in fact, for one of these homogeneous ones to have sort of a free Syzygy module, it happens, but it's very rare. So you have to be really lucky. And so in particular, there's no homogeneous mu basis. So that's why in this case, if I want to think about this sort of mu technology, I really have to work in the affine setting. And but notice I can still talk about the resultant of a mu basis. And again, when I turn my polynomials, or when I turn the Syzygies, into the moving planes, I get this. And so each of these, it's a polynomial in S and T, and the coefficients are linear in X, Y, Z, same for the others. So when I take this resultant, so this is now a genuine multi-polynomial resultant. We were beyond what the Sylvester determinant can do, because I really have 3 polynomials, and so it's a polynomial but this does eliminate S and T, so it's a polynomial in X, Y, Z, and so I'm just going to write it more simply as that resultant. And it turns out the resultant does vanish on the parameterized surface. Because remember, in the curve case, when I took the resultant of a mu basis, I got the implicit equation to a power. And so the question is, how close are we to that here? So here's some first indication, well, this guy at least vanishes on the surface, but that's not quite the whole story, because it may vanish in other places as well. In fact, it may vanish in lots of other places. So we're going to see that this is a slightly problematic object. So let's do 2 examples. So here's this one where we had the mu basis, and if you actually compute the resultant, what you get is you actually get the implicit equation, but you get this fudge factor. And yet this is a case with no base point. So what's this fudge factor? And it's basically something that arises from the fact that it's not a mu basis homogeneously. So this is sort of telling you that I have a mu basis that works affinely, but it doesn't work when I make things homogeneous. And so you definitely will get an extraneous factor in some cases. And we'll see other ways in which you get some extraneous factors as well. But then if you take this one, where this little parameterization, turns out 0, 0 is obviously a base point because it makes everything vanish. And it turns out when you compute you can compute a mu basis, and the resultant is just identically 0. So it just totally collapses. And so basically what happens is, in this case, the result of the mu basis literally tells you nothing about what's going on. And what we'll see is that's because this is a really bad base point.
It doesn't tell you it's a really bad base point.
It tells you that's true. It tells you it's a really bad base point. Okay.
Is that because that's the Sylvester resultant? You need like a torque one or something?
Yeah. So this is the classic multi-polynomial resultant.
You need some sparse version.
And but even a sparse version wouldn't help.
Oh, okay.
So this guy's just bad. And so what I'm going to do, so we got problems, but it's still there's something actually nice going on. So what I want to do is do an analysis that convinces you, in spite of all this complications, there's something really fun. And so here's the point, is, what's supposed to happen? So when is a resultant supposed to vanish? Well, it's basically, this is supposed to tell me that, these equations have a solution in our parameters s and t. And that, might possibly happen at infinity. And, and again, here I'm taking the fact that I actually might, use some funky compactification. So, it might be P2 or P1 cross P1 or some toric one. And, but the idea is that, I'm looking at this kind of situation. So this polynomial vanishes if I can find an s and a t that make these guys vanish. So that's what we're thinking about. So let's assume that we're away from a base point. And remember that, so here I'm thinking of this as this matrix, and remember that A, B, C, D, my parameterization, are the 3 by 3 minors of this. If I'm away from a base point, that means at least one of these guys is non-vanishing. That means this guy has rank 3 because one of its minors is non-zero. So that means that when I think of these as defining planes, they're linearly independent. And so the picture I get is that I get my 3 moving planes at this particular point. They actually intersect at a point. And so away from the base points, the moving planes have a unique point of intersection. Of course, that's on the surface because that point follows each of the planes. So this is what we saw in the curve case when we had the 2 moving lines intersect at a point. That point was a point on the curve. Here are 3 planes intersect at a point, and that point's on the curve. So, and basically, as we vary the parameters s and t, these guys will move around, and this point will move around. I'll be tracing the surface. That's the picture we want. We really like that. But now what happens at a base point? So in this case, the parameter blows up to an exceptional curve on the surface. And exceptional curves come in 3 flavors. It might be an actual just line that lies on the surface. It might be a plane curve that lies on the surface, or it might actually be a space curve. On the other hand, at a base point, our matrix drops rank. So it's no longer rank 3 because, again, the 3 by 3 minors of this all vanish. And so that means the rank is either 2, 1, or 0. And it turns out the wonderful fact is that this 2, 1, or 0 matches up precisely with those 3 possibilities. So what I'm going to do is sort of work through each of those separately to see what's going on. So at a rank 2 base point, so that means that I really have only 2 independent planes, and the third one is sort of a linear combination of the other 2. So I get a picture that looks like this. P is 0, Q is 0, R is 0. And they intersect at a line, and of course that line is the exceptional curve that happens in this case. So we have the exceptional curve as a line, and notice that, but that line's on the surface. So my resultant here is still vanishing exactly on the surface. So life is really nice. And so, and furthermore, when you look at this sort of from an algebraic point of view, a base point has rank 2. It means that locally this ideal can actually be generated by 2 elements, and that's what we call a local complete intersection. And we really love local complete intersections. So that's basically, if you're going to have a base point, that's the nicest possible base point, and that's the rank 2 base point. So that's really nice. Now, what happens at a rank 1 base point? Well, that matrix has rank 1, which basically says the 3 moving planes all actually coincide at a point. And so basically, all 3 of these are all coincide. And what happens is that the exceptional curve, this is the case where the exceptional curve is a plane curve, and it lies in this plane given by the 3 moving planes. But what happens is that at any point here, this ST, any point in this whole plane makes these guys vanish. That means the resultant vanishes on the equation on this entire plane. So if I take the equation of the plane, this is going to be a factor of the resultant. And the question is, what's the exponent? And that's where a theorem comes in. And so it turns out, because remember that a base point has a Hilbert-Samuel multiplicity. It's a fairly sophisticated object. But also in this situation, you have sort of a more naive notion of multiplicity, where you just take the ideal and mod out your structure one. You do it locally at the point P. Turns out this is a finite dimensional vector space and just the dimension of that. And so that's sort of a more naive multiplicity, and it's the difference. And what happens is that at a base point of rank 1, then what happens here is that it locally requires 3 generators. So you have one more, because you're sort of in a 2-dimensional ring, so you have sort of one more than what you need for a complete intersection. So this is an almost complete intersection. And what happens is that in a complete intersection, you can also define these 2 numbers, but for a local complete intersection, they're the same. And so the point is that right here at an almost complete intersection, then they become differents. And so basically that difference sort of measures sort of how far you are from being a complete intersection. And so that's really nice. So the idea is that we know we're acquiring an extraneous factor. And then what about rank 0 base point? Well, that's pretty spectacular. So that means that our matrix ABCD consists entirely of zeros. That means that what I've been calling a moving plane, all of its coefficients vanish. So each moving plane is the entire space. And so in particular, and that's the case when the exceptional curve is a space curve, because it can't fit on any plane. So it actually has to fit on the whole space. And so, but the point is that, and so at any point in the space, well, the three moving planes vanish because all their coefficients are 0, like duh. And so that means, so this is the case where the resultant vanishes identically. And this is why I don't think it matters what kind of resultant you use. That basically, this local behavior is enough to just kill it.
How do you compute the space curve? You know?
Well, the Riesz algebra. Because you think about it, when we take proj of the Riesz algebra, that's going to give you what I think it's what they call this, Lynn, is it what they call the special fiber or something? And so it's when you sort of take that and include it in the space. So that information is in the Riesz algebra. But to find out what's really going on, I have to ask a real commutative algebraist. And also what happens in this case is that a base point has rank 0. That means that locally your ideal requires 4 generators. And of course, notice I have 4, but the idea is that I can't dispense with any of them. I'm stuck with all 4. And that's what happens in our earlier example. Because here's our base point, and we take our 4 polynomials. Remember, I want to represent them in this way, because I can represent it this way, but I want to represent them with a common denominator. And so I have that, and the t cubed. That gives me that ideal. You do a little, I can basically, the t to the 4th I can get rid of because of that. I get this, and that's just the cube of the maximal ideal. And what happens is that I can't get rid of any of these. And even after localization, I'm still stuck with 4. And so basically that shows why I have a rank 0 base point, and that's sort of the explanation of why the resultant vanishes completely. So where are we, and what do we want? Because we've got all these problems, and so what do we have? We have this resultant. So let's first of all assume that the base points are at worst local, almost complete intersections. So we don't have any rank 0 base points. If the base points are all rank 1 or 2, well then we have our resultant. It's going to have this kind of thing, and it's going to have some of these extraneous factors that come from the rank 1 base points, but then we also might have this extraneous factor that comes from infinity. And it turns out that Bouzet, Chardin, and Joannelou have worked out what that is. They're also the folks that proved that that's the right exponent. And but what happens, of course, remember, this is not easy to compute, the mu basis. Its resultant is also not easy to compute, and this extraneous factor is just deeply irritating. And what we want is the stuff in the middle, because that's actually really nice. And of course, remember the notation here is that, the EP and DP, that's short for these multiplicities. LP, that's the plane that contains the exceptional curve in the rank 1 case. And then just a reminder that, of these two multiplicities, this one's always greater than or equal to that one, and the local complete intersection case is exactly when they're equal. And so the idea is these really are the rank 1s where that's actually to a positive power. So the question is, how do we get what we want? Well, we abandon mu bases, we abandon resultants, and we just go to a matrix representation. And so the beautiful theorem is that we're going to see in the next slide is there's a matrix representation of this guy that is basically built just from moving planes. And so we're going to basically get this center part right here in a really easy way, and that's something we really like. So what's a matrix representation? So I'll take a homogeneous polynomial, and I'm going to say it's represented by a matrix M of homogeneous polynomials. And so basically, so geometrically what I want is I want the rank of the matrix, because remember that the matrix involves x, y, z, w, so if I plug in a point in projective space, I want that matrix to drop rank precisely when evaluated at points on the surface defined by h equals 0. And so that's geometrically what it means, but I actually want something slightly stronger because I really want h to be the GCD of the maximal minors of M. So that's the algebraic condition that I want to be true. And so the theorem of Ization, Chardin, and Joannolou from 2009 says that in the situation that we're in, homogeneous degree n, base points at worst almost local almost complete intersections, let's assume we're algebraically closed. Then what I want to do is I need to pick some syzygies of the appropriate degree. So I pick a nu greater than or equal to 2 times n minus 1. And then I look at syzygies in that degree, and I pick a basis. And so in this case, they're basically 4 tuples of polynomials of degree nu, and then I basically take the dot product and turn them into the moving planes. So I get a bunch of moving planes. I get capital N of them. And then I basically take each one of the moving planes and I sort of write it in terms of the binomials of degree nu, and that's the matrix of coefficients. And so that's the matrix that we can build just from these moving lines. So here's a matrix of linear forms, and the theorem is, with these hypotheses, it represents exactly that gadget that we want. And so that's how the matrix representation really fills the role caused by the lack of a mu basis in a homogeneous sense. And so you sort of have to back away from stuff. And so again, this matrix, you can think about it in 2 ways. You can think about it as just the matrix itself, or you can think about the GCD of maximal minors. And so in one sense, this replaces the resultant, but what happens is the matrix itself is a useful gadget. So just to say a few words about that, because this idea of, because when we have a matrix, dropping rank, it's an idea that goes back quite a ways. And also, if I were to apply this idea in the curve case with my nu equal to n minus 1, then my matrix, that's exactly the square matrix we got in the curve case. The syzygies of ABC in degree n minus 1, and that square matrix that it computed the result into the mu basis. So what we have is, we've had to abandon the result of the mu basis, but we find that the matrix generalizes perfectly. Just that, in this case, it happened to be a square matrix. In our situation now, it's a rectangular matrix. The proof is more complicated because it actually uses its approximation complex. So again, it's this tension between the Riesz algebra and the symmetric algebra. And again, we'll hear a little bit more about this in Hal's lecture. These approximation complexes were invented in the early 1980s, and they were first applied to the geometric modeling context by Bouvet and Joannolou about 20 years later. And then these have actually had applications. And so, for example, if you want to study an intersection between a curve and a surface, well, you represent the surface by one of these matrices, and then you can understand how the curve meets the surface by asking some rank-dopping questions once you add in this extra question about what the curve is. And so Ba, Bouzet, and Morin did that in 2009. And then also, for the surface-to-surface intersection, you represent one of the surfaces parametrically, you represent the other surface by a matrix. And again, understanding the interaction of that, you can try to get a sense of where do these two surfaces meet, and that's Ba and Bouzet in 2012. So there's actually some applications, some geometric applications of this, where basically you represent the surface using this matrix. And then also here I was giving a version that was basically using P2 as the domain. There's also a version where you use P1, or you can use the toric surface of the Newton polygon of ABCD. And so to finish off, let me just go back to the slide we saw on Monday from the paper by Botbol and Dickenstein. So we want to do some elimination here. So here's our ABCD. But now we're not going to make many. What they wanted to do is try to give something that was practical and could be stated without too much difficulty. And practically, you might not, you don't want to have to worry about what kind of polynomials you have. So you just take a polygon, a lattice polygon that, so that should be R, that should be R2, that's a typo. So you take a lattice polygon that contains the Newton polygons of all ABCD. And so the idea is you just want to make sure that, and you typically take the smallest, but don't always, so you just take a polygon that does that, and then you play the Syzygy game. So you take, our moving lines. I'm working projectively because of W, and the idea is that, and in fact, if you think about it, this kind of combination, because I'm going to replace these with our, the polynomials ABCD. So these are actually the special polynomials that go all the way back to Bezout in 1779, and you wanted to pick them carefully. And here, picking them carefully means that you want a degree restriction, and so you want A, B, C, and D to. In this case, you want them to be contained in their Newton polytopes in 2 times the polytope, and of course you want them to be Syzygies. And then you take a basis of, and of course any one of these you can. Any one of these guys, you can play our game of writing as a polynomial in S and T with with coefficients that are linear in X, Y, Z, and then I use a basis of those to create a matrix of linear forms. And again, lurking behind this is all the approximation complex and stuff like that. And of course, what I said on Monday is in nice cases. But remember, what I want is I want the rank of this matrix to drop precisely when evaluated at the surface. So I want just the surface, no extraneous factors. So what that means is I want all my, so I might have base points, but I don't want any rank 0 base points because of course they kill me. And also a rank 1 base point, an almost local complete intersection, that would give me an extraneous linear factor. I don't want that. So if I want to get the surface itself, my base points have to be local complete intersections. And so we now know exactly the context that makes this theorem work. And so to finish up, just to say, we've done a lot today. So notice the algebra, it's a very different flavor from the geometry that we did last time. If you think about the pictures and the cool stuff, there were some pictures here, but the algebra was really much more dominant. And notice that we saw some toric varieties, and so those appeared. We saw some elimination theory, and also with the curved surface and surface-surface intersection, there's actually some numerical linear algebra working there in what you have to do with those algorithms. So there's a lot of stuff that's tied up in this. And so I wanted to show you some of the algebra. It's not all of it. So like I say, you'll see some more with Hal this afternoon. And so that's going to be what Hal does. And then tomorrow we do rigidity theory. So that's it for today. And you'll notice I did need the extra 5 minutes.
15 seconds.
Yeah. So any questions? Yeah.
So how important is it that the base point in this situation is exactly co-dimension 2 with dimension 0 for this one polygon? Like if I want to generalize this to higher dimensions, like what kind of things here generalize and what kind of things here don't?
Yeah, and so the answer is I don't really know that as well as I should.
It
So-
becomes really hard when you don't have zero dimension. You might have thought, oh, it's just codimension too. It's not. It's the, I mean, you really need zero dimensional base look. It's really.
Yeah.
If I just say codimension to color.
No, you'd hope so. That's exactly what you would bet, and you'd be wrong.
But this is the kind of stuff that, like if you get a chance to go to Europe and visit India, you want to talk to people like Laurent Bouzet, because he knows this stuff really well. And he could probably give you a much better answer to this question.